So, let's start. Number 10. The Sloan Great Wall. Picture something so impossibly massive that even if you could somehow hop aboard a beam of light and ride it at 186,000 miles per second, it would still take you over 1 billion years just to travel from one end to the other. That's the Sloan Great Wall, a cosmic structure so staggeringly enormous that when scientists first discovered it, they had to triple-check their calculations because they couldn't believe what they were seeing. This thing is one of the largest known structures in the observable universe, and honestly, it probably shouldn't even be possible. Discovered back in 2003 by a team of astronomers analyzing data from the Sloan Digital Sky Survey, this cosmic wall stretches approximately 1.4 billion light-years across space. To put that in perspective, that's genuinely hard to grasp. Our entire Milky Way galaxy, with its 200 to 400 billion stars, is only about 100,000 light-years wide. The Sloan Great Wall is 14,000 times longer than our galaxy is wide. Wrap your head around that for a moment. What exactly is this Great Wall made of? Well, it's essentially a superstructure of galaxies, a filament in what cosmologists call the cosmic web. Imagine billions upon billions of galaxies, each containing billions of stars, all strung together by gravity like pearls on an incomprehensibly long string. These galaxies aren't just randomly scattered either. They're organized, connected, forming what looks like a wall when we map them out. Between these filaments are vast voids, enormous empty spaces where almost nothing exists. The universe, it turns out, looks a bit like Swiss cheese on the largest scales, with matter concentrated in these web-like structures and empty bubbles in between. But here's where things get really strange. According to our current understanding of cosmology, specifically something called the cosmological principle, the universe should be roughly uniform when you look at it on large enough scales, meaning, if you zoom out far enough, everything should look pretty much the same in every direction. No region should be dramatically different from another. The Sloan Great Wall violates this principle. It's too big, too organized, too connected. Some scientists have argued that structures this large shouldn't exist, given the age of the universe and the laws of physics as we understand them. Think about it this way. The universe is about 13.8 billion years old. That sounds like a lot of time, and it is, but gravity works slowly on cosmic scales. For something as massive as the Sloan Great Wall to have formed, gravity would have needed to pull all those galaxies together over billions of years. The problem is, the universe has also been expanding that entire time, working against gravity's pull. So how did this structure get so large and so organized so quickly? That's the mystery that keeps cosmologists up at night. Some researchers have proposed that the Sloan Great Wall might be evidence of something we don't yet understand about the early universe. Perhaps there were density fluctuations in the primordial soup of matter right after the Big Bang that were larger than we thought. Maybe dark matter, that mysterious invisible substance that makes up most of the universe's mass, played a more active role in structure formation than our models predict. Or perhaps, and this is the unsettling possibility, our entire understanding of how the universe evolved needs revision. If you could somehow step outside the universe and look at it like a three-dimensional map, the Sloan Great Wall would appear as a glowing thread, weaving through the darkness, connecting countless points of light. Each point would be a galaxy. Each galaxy would contain hundreds of billions of stars, and around many of those stars would orbit planets. Some of those planets might harbor life. Intelligent civilizations could exist on worlds within the Sloan Great Wall right now, looking up at their own night skies, asking the same questions we are. They might even be studying the same structure we are, from a different vantage point, completely unaware of our existence. The discovery of the Sloan Great Wall forced astronomers to reconsider what they thought they knew about the universe's architecture. Before we found structures like this, we assumed there was a limit to how large cosmic structures could grow. We thought we understood the rules, but the universe has a habit of ignoring our assumptions. Every time we build a bigger telescope, peer deeper into space, or analyze more data, we find something that makes us scratch our heads and go back to the drawing board. And here's something truly mind-bending to consider. The Sloan Great Wall is only the largest structure we've found so far. Emphasis on so far. Our telescopes can only see so much. The observable universe has limits. not because the universe ends there, but because light from beyond a certain distance hasn't had time to reach us yet. Out beyond what we can see, there could be structures even larger than the Sloan Great Wall. There could be cosmic architecture on scales we can't even imagine, following patterns we haven't discovered, governed by forces we don't yet understand. When you look up at the night sky and see the stars twinkling above you, you're seeing the tiniest fraction of what's out there. Those stars are part of our galaxy, which is part of our local group of galaxies, which is part of a larger supercluster, which itself is part of these enormous filaments, like the Sloan Great Wall. We're living inside a cosmic structure so vast that our entire planet, our solar system, our galaxy, is less than a speck of dust in comparison. And yet, from that tiny vantage point, we've managed to map these structures, measure them, and try to understand how they came to be. That's pretty remarkable when you think about it. Number 9. Stephenson 2-18, the hypergiant star. If you think the sun is big, think again. Our sun is actually pretty average when it comes to stars, maybe even a bit small compared to some of the monsters lurking out there in the cosmos. And when it comes to truly gargantuan stars, few can compete with Stephenson 2-18. This absolute unit of a star is one of the largest known stars in the entire universe, and if we're being honest, it makes our sun look like a grain of sand on a beach. Stephenson 2-18 is what astronomers call a red supergiant, or more specifically, a red hypergiant. It's located about 19,000 light-years away from Earth in the constellation Scutum, nestled within a massive star cluster called Stephenson 2. This cluster is home to several enormous stars, but Stephenson 2-18 is the heavyweight champion among them. The exact size is difficult to pin down because stars like this don't have solid surfaces, and their outer atmospheres are diffuse and constantly fluctuating. But estimates suggest that Stephenson 2-18 has a radius roughly 150 times larger than our Sun. Let that sink in for a moment. If you place Stephenson 2-18 at the center of our solar system where the Sun currently sits, its surface would extend beyond the orbit of Saturn. Jupiter, the largest planet in our solar system, would be inside this star. Earth, Mars, the asteroid belt, all of them would be engulfed, vaporized, consumed within the outer layers of this stellar behemoth. Standing on Earth, if Earth could somehow exist that close, you wouldn't see a sun in the sky. You would be inside the sun. The entire sky would glow with angry red light in every direction. But despite its enormous size, Stephenson 2-18 isn't actually the most massive star out there in terms of weight. That might sound contradictory, but here's the thing. Stars can be large without being particularly dense. Red hypergiants like Stephenson 2-18 have reached a late stage in their life cycle. They've exhausted much of the hydrogen fuel in their cores and have expanded outward, becoming bloated and diffuse. The outer layers of these stars are incredibly thin, almost like a hot, glowing fog. If you could somehow scoop up a bucket of material from the surface of Stephenson 2-18, it would weigh less than a bucket of air here on Earth. Yes, the star is enormous, but it's not packed tight with matter like younger, more compact stars. The actual mass of Stephenson 2-18 is estimated to be somewhere around 12 to 25 times the mass of our Sun. That sounds like a lot, and it is, but there are stars out there that weigh much more. Some of the most massive stars known can have masses exceeding 100 times that of the Sun. But they're much smaller in size because they're still burning hot and bright and haven't reached that bloated red hypergiant phase yet. So when it comes to stars, bigger doesn't always mean heavier. It's one of those cosmic quirks that can mess with your intuition. Stars like Stephenson 2-18 don't live long lives, at least not compared to smaller stars. Our Sun, for instance, has a lifespan of about 10 billion years. It's currently around 4.6 billion years old, so it's got plenty of time left. But massive stars burn through their fuel much faster. They live fast and die young, cosmically speaking. A star like Stephenson 2-18 might only exist for a few million years before it runs out of fuel and meets a violent end. And when a star this massive dies, it doesn't go quietly. It explodes in what's called a supernova, one of the most energetic events in the universe. But even before it reaches that dramatic conclusion, Stephenson 2-18 is already shedding enormous amounts of material. Red hypergiants are incredibly unstable. Their outer layers are so loosely bound that they're constantly puffing off gas and dust into space. This creates a massive nebula around the star, a glowing cloud of material that will eventually drift away and become the building blocks for new stars and planets. In a way, stars like this are cosmic recycling plants. They take the hydrogen and helium that's been around since the Big Bang, fuse it into heavier elements like carbon, oxygen, and iron, and then scatter those elements back into space when they die. Every atom in your body, every element that makes up Earth, was forged inside a star like this at some point in the distant past. If you could somehow observe Stephenson 2-18 up close from a safe distance, of course because getting too near would be instantly fatal, you'd witness a spectacle unlike anything in our solar system. The star would dominate your view. A massive, glowing red sphere that pulses and flickers as convection currents churn through its outer layers. Enormous plumes of hot gas would rise from the surface, cool, and then sink back down in a slow, mesmerizing dance. The light from the star would be dim by stellar standards, most of its energy radiating in infrared wavelengths that are invisible to human eyes. But if you could see infrared, the star would blaze with an eerie, otherworldly glow. Around the star, you might see remnants of previous eruptions, shells of gas and dust that were expelled thousands or tens of thousands of years ago. These shells would glow faintly, illuminated by the star's light, creating nested layers of nebulosity that extend for light years in every direction. And somewhere in that hazy glow, new stars might already be forming, condensing from the material that Stephenson 2-18 is cast off. The death of one star seeds the birth of others. It's a beautiful cycle, even if it's happening on a scale that's hard for our human minds to fully appreciate. Astronomers study stars like Stephenson 2-18 not just because they're interesting in their own right, but because they help us understand the life cycles of massive stars. These stellar giants are rare. Most stars in the universe are small, cool, red dwarfs that will burn for trillions of years. But the rare massive stars, the ones that grow into red hypergiants, play an outsized role in shaping the universe. They produce the heavy elements necessary for planets and life. They sculpt the interstellar medium with their powerful winds and explosive deaths. And they serve as cosmic laboratories, where the laws of physics are pushed to their limits. When Stephenson 2-18 finally does explode, and it will, possibly within the next few 100,000 years, though predicting the exact timing is impossible, the explosion will be visible from Earth even though it's 19,000 light-years away. For a few weeks or months, it will shine as brightly as a full moon in the night sky, and it will be visible during the daytime. Ancient humans might have witnessed supernovae like this and interpreted them as omens or divine signs. Today, we know they're the death throes of massive stars, but that doesn't make them any less awe-inspiring. And here's a sobering thought. By the time we see Stephenson 2-18 explode, assuming we're still around to witness it, that explosion will have already happened 19,000 years ago. The light will have been traveling through space for nearly 200 centuries before it finally reaches our eyes. We're always looking into the past when we look at the stars. The farther away something is, the older the light we're seeing. In a very real sense, astronomy is the study of history. Every photon that enters our telescopes is a messenger from the past, carrying information about events that happened long before we existed. Number 8. The Borealis void, the great cosmic nothing. Space is mostly empty. We know that. The distances between stars are vast, the distances between galaxies even more so. But when astronomers talk about voids, they're referring to something different. They're talking about regions of space that are even emptier than the already mostly empty universe. And among these voids, one of the most striking is the Borealis void, also charmingly nicknamed the Great Nothing. Discovered in 1981 by astronomer Robert Kirshner and his colleagues, the Borealis void is a roughly spherical region of space that contains far fewer galaxies than you'd expect. It's located about 700 million light-years away from Earth, in the direction of the constellation Borealis. The void spans approximately 330 million light-years in diameter. That's not quite as large as some of the other structures we've talked about, but what makes it remarkable isn't its size. It's what's missing. In a typical region of space this large, you'd expect to find around 2,000 galaxies. The Borealis void contains only about 60. That's a 97% deficit. Imagine walking through a city and finding that 97% of the buildings are missing. That's basically what astronomers stumbled upon when they mapped this region. It's not that the void is completely empty. There are a few galaxies scattered throughout it, but it's so underpopulated compared to surrounding regions that it stands out dramatically when you map the cosmic web. The existence of voids like Borealis challenges our understanding of how structure forms in the universe. After the Big Bang, matter wasn't distributed perfectly evenly. There were tiny fluctuations, regions that were slightly denser than others. Over billions of years, gravity amplified these differences. Dense regions attracted more matter and became denser still, eventually forming galaxies and galaxy clusters. The less dense regions lost matter to these gravitational attractors and became even emptier, forming voids. But the Borealis void is so large and so empty that it raises questions. How did such a massive region become so devoid of galaxies? Was there something about the initial conditions in this part of the universe that made it particularly underdense? Or did something else happen here, some cosmic event we don't understand, that cleared out the galaxies? One theory suggests that voids grow over time through a process that's basically the opposite of gravitational collapse. As matter gets pulled into the denser filaments and walls that make up the cosmic web, the voids between them expand. It's like stretching a piece of fabric. The threads stay connected, but the holes between them get bigger. The Borealis void might simply be a region where this process happened more efficiently than elsewhere, creating an exceptionally large and empty bubble in the cosmic foam. Another possibility, and this one's more speculative, is that the void represents a region where dark energy, the mysterious force causing the universe's expansion to accelerate, might be slightly stronger or behave differently than elsewhere. Dark energy is already one of the biggest mysteries in physics. We know it exists because we can measure its effects, but we don't know what it is. If dark energy strength varies from place to place, even slightly, that could affect how structure forms. A region with slightly stronger dark energy would expand faster, making it harder for gravity to pull matter together, potentially creating a void. What would it be like to exist inside the Borealis void? If you were standing on a planet orbiting a star in one of those 60 lonely galaxies, your night sky would be strikingly different from ours. When we look up at night, we see our own Milky Way galaxy stretched across the sky as a band of light. We see a few nearby galaxies like Andromeda if we know where to look. But from inside the Borealis void, you'd see almost nothing. Your own galaxy would still be there, of course. But beyond that, the sky would be eerily empty. No nearby galaxies, no clusters, no cosmic landmarks. Just darkness stretching in every direction for hundreds of millions of light years. It would be the ultimate cosmic isolation. Any civilization that evolved in the Borealis void would have a fundamentally different view of the universe than we do. They might not even realize for a long time that galaxies exist in abundance elsewhere. Their astronomers would look out into space and see mostly darkness, leading them to potentially very different conclusions about the nature and structure of the cosmos. It's a humbling reminder that our understanding of the universe is shaped by our location within it. We happen to live in a relatively dense region, surrounded by other galaxies. We're cosmologically lucky. The Borealis void also connects to a larger question about the fate of the universe. The cosmic web of filaments, walls, and voids that we observe today is still evolving. Voids are growing, filaments are becoming more pronounced, and galaxies continue to merge and cluster together. Billions of years from now, the universe will look different than it does today. The voids will be larger, the filaments might be more prominent, and the overall structure will continue to evolve as the universe expands. But there's a catch. The universe isn't just expanding. It's expanding faster and faster, accelerated by dark energy. Eventually, if this acceleration continues, galaxies that aren't already gravitationally bound together will drift so far apart that they'll disappear beyond each other's cosmic horizons. Civilizations in the far future, trillions of years from now, will look out into space and see even less than a civilization in the Boetes void sees today. They'll see their own galaxy, maybe a few neighbors that have merged with it, and beyond that, nothing but darkness. The evidence of the Big Bang, the cosmic microwave background radiation, will have faded and cooled to the point of being undetectable. Future astronomers won't be able to see the expanding universe because everything will have already expanded beyond visibility. In that distant future, if intelligent beings arise and try to study the cosmos, they'll come to the conclusion that the universe consists of a single galaxy surrounded by infinite empty space. They'll have no way to know about the billions of other galaxies that once existed, no way to discover the Big Bang, no way to understand that the universe had a beginning. They'll essentially be living in a cosmic void by default, and their scientific knowledge will be limited by what they can observe. We, on the other hand, live in a special time. We exist at a moment in cosmic history when the universe has expanded enough to create large-scale structure and diversity, but not so much that everything has disappeared beyond our view. We can see the cosmic web. We can detect the afterglow of the Big Bang. We can study the history and evolution of the universe. The Boetes void reminds us that our cosmic perspective is both precious and temporary. Number 7. Sagittarius A*, the monster at the heart of home. Every galaxy has secrets, but some are darker than others. Literally, at the very center of our Milky Way galaxy, hidden behind vast clouds of gas and dust, lurks something that sounds like it came from a science fiction nightmare. A supermassive black hole. Its name is Sagittarius A*, pronounced Sagittarius A*, and it's been quietly sitting there for billions of years, anchoring our entire galaxy with its immense gravitational pull. Sagittarius A times weighs in at about 4 million times the mass of our Sun. That's a lot of mass compressed into a region smaller than Mercury's orbit. To call it dense doesn't do it justice. This is matter compressed to a point where the laws of physics, as we understand them, break down. At the center of the black hole is what scientists call a singularity, a point of infinite density where space and time become meaningless. But we can't see the singularity directly. It's hidden behind something called the event horizon, the point of no return beyond which nothing, not even light, can escape. For decades, we knew Sagittarius A times was there because we could see its effects on nearby stars. Astronomers tracked stars orbiting the galactic center and noticed they were moving incredibly fast, following elliptical paths that brought them swooping past something invisible. By measuring the speeds and orbits of these stars, scientists calculated the mass of whatever they were orbiting. The only explanation that made sense was a supermassive black hole. This work was so significant that Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics in 2020 for their observations of Sagittarius A*. But actually, imaging the black hole itself was a different challenge entirely. You can't see a black hole directly because it doesn't emit light. What you can see, though, is the glowing material around it. Matter falling toward a black hole gets compressed and heated to extreme temperatures, sometimes millions or even billions of degrees. This superheated material emits radiation, particularly in radio wavelengths, creating a bright glow around the dark shadow of the event horizon. In 2022, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A*. It showed a bright ring of emission surrounding a dark central region, the shadow of the black hole itself. The image was blurry and fuzzy by everyday standards, but it was extraordinary for what it represented. We had, for the first time, photographed the black hole at the center of our own galaxy. The achievement required coordinating radio telescopes from around the entire planet, effectively turning Earth itself into one gigantic telescope. The data processing alone took years. Looking at that image is surreal. That dark circle in the center represents the edge of a region where space-time is so warped that nothing can escape. It's a one-way door to nowhere, or maybe to somewhere we can't even conceive of. Every bit of matter that crosses the event horizon is lost to our universe forever, adding to the black hole's mass but disappearing from our reality. It's the ultimate cosmic trash compactor, except there's no bottom. There's no other side where the trash comes out. It's just gone. Despite its tremendous mass, Sagittarius A times is actually relatively quiet compared to some supermassive black holes in other galaxies. Some black holes are actively feeding, consuming vast amounts of material, and shooting out powerful jets of energy that can extend for thousands of light years. These are called active galactic nuclei, or quasars if they're particularly bright. Sagittarius A*, by contrast, is mostly starving. There isn't much material in its immediate vicinity to consume, so it just sits there, dark and patient, occasionally gulping down a stray cloud of gas or an unlucky star that wanders too close. But don't let its current quiet demeanor fool you. Sagittarius A times has a violent past. Evidence suggests that the Milky Way's center was much more active millions of years ago. In 2020, astronomers discovered enormous structures called Fermi bubbles extending 25,000 light-years above and below the galactic plane. These bubbles are thought to be remnants of a massive eruption from Sagittarius A times that occurred a few million years ago, possibly when the black hole consumed a large amount of material in a short time. The explosion sent shock waves and radiation billowing outward, creating these vast, glowing bubbles that we can still detect today. Imagine witnessing that event from Earth. If Earth had existed back then with life capable of seeing it, the entire center of the galaxy would have lit up, possibly outshining all the stars in the sky combined. High-energy radiation would have bathed the inner regions of the galaxy. Any civilizations within a few thousand light-years of the galactic center would have been sterilized by the blast. Even at our safe distance of about 26,000 light-years, we might have seen spectacular auroras as particles from the eruption slammed into Earth's atmosphere. The stars closest to Sagittarius A times lead precarious lives. There's a population of stars known as the stars, short-period stars that orbit extremely close to the black hole. One of them, called S2, has an orbital period of just 16 years and approaches to within 17 light hours of the event horizon. That's closer than the distance from the Sun to Uranus. At its closest approach, S2 is traveling at nearly 3% of the speed of light. The gravitational forces it experiences are intense, and astronomers have been able to use its orbit to test Einstein's theory of general relativity in an extreme environment. So far, Einstein's theory holds up perfectly, even in the warped space-time around a supermassive black hole. What happens if you fall into a black hole? Well, it's not pleasant, and it's definitely not survivable, but the experience would be bizarre. As you fell toward the event horizon, time dilation effects would kick in. From your perspective, you'd cross the horizon in finite time. But to an outside observer watching you fall, you'd appear to slow down, getting dimmer and redder as you approach the point of no return. They'd never actually see you cross the horizon. You'd appear to freeze just outside it, your image gradually fading from view. Meanwhile, from your perspective, things would look very different. As you fell, tidal forces would stretch you. The gravity pulling on your feet would be stronger than the gravity pulling on your head, assuming you're falling feet first. This difference would stretch you like taffy, in a process astronomers cheerfully call spaghettification. For a black hole as large as Sagittarius A*, you might actually survive crossing the event horizon intact because the tidal forces at the horizon are relatively weak for such a massive black hole. But don't get too excited. Once you're inside, you're doomed. All paths lead to the singularity, and you'd be torn apart by ever-increasing tidal forces before you got there. Black holes also raise profound questions about information. According to quantum mechanics, information can't be destroyed. But if something falls into a black hole and is lost forever, what happens to the information it carried? This is called the black hole information paradox, and it's been bothering physicists for decades. Stephen Hawking proposed that black holes aren't completely black. They emit a faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over unimaginably long timescales, a black hole could theoretically evaporate completely through this radiation. But does the Hawking radiation carry the information about what fell in, or is the information truly lost? We still don't know. And the answer might require a theory that successfully merges quantum mechanics and general relativity, something we don't yet have. Sagittarius A times will be around for a long, long time. In fact, barring any unexpected cosmic disasters, it will outlive our sun, our solar system, possibly even our galaxy in its current form. Billions of years from now, the Milky Way will collide and merge with the Andromeda Galaxy. When that happens, Sagittarius A times will eventually merge with Andromeda's supermassive black hole, creating an even larger black hole at the center of the merged galaxy. The collision will trigger a spectacular burst of star formation and probably activate both black holes, turning them into powerful quasars for a time as they consume the gas and dust stirred up by the merger. And we live in orbit around this thing. Our entire solar system, along with hundreds of billions of other star systems, orbits Sagittarius A*. We're all bound to it by gravity, circling it like moths around a dark flame. It takes our sun about 230 million years to complete one orbit around the galactic center. Dinosaurs roamed Earth the last time we were on the opposite side of the galaxy. Next time we complete an orbit, who knows what Earth will look like, if it even still exists. Number 6. The Great Attractor, the cosmic mystery pulling us home. Galaxies don't just sit still in space. They move. They orbit within galaxy clusters. They drift through intergalactic space, and sometimes they crash into each other. But there's one motion that's particularly strange, and it took astronomers decades to figure out what was causing it. Our Milky Way galaxy, along with thousands of other galaxies in our cosmic neighborhood, is being pulled toward something massive, something hidden, something we call the Great Attractor. The Great Attractor is a gravitational anomaly located roughly 150 to 250 million light-years away in the direction of the constellations Triangulum, Austral, and Norma. It's difficult to observe directly because it lies in what astronomers call the zone of avoidance, the region of sky obscured by the Milky Way's own disk. All the stars, gas, and dust in our galaxy block our view of what's beyond in that direction, making it extremely challenging to study. But we know the Great Attractor is there because we can measure its gravitational effects. By studying the motion of galaxies in our region of space, astronomers notice something odd. Our local group of galaxies, which includes the Milky Way and Andromeda, is moving toward a specific point in space at about 600 kilometers per second. That's over 1.3 million miles per hour. But we're not moving because the universe is expanding. We're moving in addition to the expansion. Something massive is pulling us. Initially, scientists thought the Great Attractor might be a massive cluster of galaxies, or a supercluster, and there is indeed a massive concentration of galaxies in that region, including the Norma cluster. But as observations improved, astronomers realized something even stranger. The Great Attractor isn't the end of the story. There's something even larger pulling on the Great Attractor itself. In 2014, astronomers mapped out a supercluster they named Laniakea, which means immeasurable heaven in Hawaiian. Laniakea is the supercluster that contains our Milky Way, and it's defined not by proximity but by motion. All the galaxies within Laniakea are moving toward a common center of gravity. The Great Attractor is part of this flow, but it's not the final destination. The real center of Laniakea's gravitational pull is a region of dense galaxy clusters located even farther away. But wait, there's more. Beyond Laniakea, there's evidence of an even larger structure influencing galactic motion. Some astronomers have detected what they call the Shapley attractor or Shapley concentration, a massive supercluster even farther away that might be influencing the motion of Laniakea itself. It's like Russian nesting dolls of cosmic structures, each one contained within and influenced by something larger. The idea that we're being pulled toward some distant cosmic destination is both fascinating and slightly unnerving. We're all passengers on a galactic ship sailing through space toward an unknown shore, and we have no control over the journey. But don't worry about us eventually falling into the Great Attractor or Laniakea's center. The expansion of the universe, driven by dark energy, is carrying distant structures away from us faster than we're moving toward them. We'll never actually reach these far-off destinations. We're like a boat trying to sail upstream against an accelerating current. We're moving forward, but the current is pushing us backward faster, so we're actually getting farther away from our destination over time. This interplay between gravity and cosmic expansion is one of the defining features of the universe. On small scales, gravity dominates. It holds galaxies together, keeps planets orbiting stars, keeps you stuck to the surface of Earth. On intermediate scales, gravity still matters. Galaxy clusters hold together, and structures like Laniakea form as galaxies flow along gravitational paths. But on the very largest scales, dark energy wins. The expansion of space itself overwhelms gravity, causing distant structures to recede from each other faster and faster. The Great Attractor reminds us how much we still don't know about the universe's large-scale structure. For decades, it was a mystery hiding behind our galaxy's disk. Even now, with better telescopes and techniques for seeing through the zone of avoidance, we're still piecing together the full picture. What else is hidden out there? What other massive structures exist beyond our view? The universe is full of secrets, and the Great Attractor is just one of them. Number 5. The cosmic microwave background. The universe's baby picture. If you want to understand the universe, really understand it, you need to look at its earliest moments. Not through a regular telescope, those can only show us stars and galaxies. No, to see the infant universe, you need to look at something more subtle, the faint glow of radiation that fills all of space. It's called the cosmic microwave background, or CMB, and it's the oldest light in existence. The CMB is radiation left over from the Big Bang. About 380,000 years after the universe began, it had cooled enough for atoms to form. Before this moment, the universe was a hot, dense soup of particles and radiation so thick that light couldn't travel through it. But when atoms formed, the universe became transparent. Light was suddenly free to travel, and that primordial light has been traveling through space ever since. Today, that light has been stretched by the expansion of the universe from visible light into microwaves. It now has a temperature of just 2.7 degrees above absolute zero, cold enough to barely register unless you have sensitive instruments. And it's everywhere. No matter which direction you point a microwave detector, you'll see the CMB. It's the most uniform thing in the universe, varying in temperature by only about 1 part in 100,000 across the entire sky. But those tiny variations are incredibly important. They represent quantum fluctuations from the earliest moments of the universe. Tiny differences in density that eventually grew into all the structure we see today. The slightly denser regions attracted more matter and became galaxies and galaxy clusters. The slightly less dense regions became voids. The CMB is a map of the seeds of cosmic structure. The discovery of the CMB in 1965 was one of the most important moments in the history of astronomy. Two scientists, Arno Penzias and Robert Wilson, were trying to get rid of annoying background noise in their radio telescope. They cleaned the equipment, even removed pigeons nesting inside, but the noise persisted. Eventually, they realized the noise wasn't noise at all. It was the echo of the Big Bang, and it was coming from every direction. They won the Nobel Prize for the discovery. Since then, we've mapped the CMB in incredible detail. Satellites like COBE, WMAP, and Planck have produced maps showing the tiny temperature variations across the entire sky. These maps have allowed us to determine the age of the universe, 13.8 billion years. Its composition, about 5% ordinary matter, 27% dark matter, 68% dark energy. And its geometry, flat, as far as we can tell. The CMB also supports the theory of cosmic inflation, the idea that the universe underwent a brief period of exponential expansion in its first fraction of a second. Inflation explains why the universe is so uniform on large scales and why it has the specific pattern of temperature variations we observe in the CMB. Without inflation, the universe would look very different, and we probably wouldn't exist. Looking at the CMB is like looking at a cosmic ultrasound, a baby picture of the universe taken when it was less than 400,000 years old. Every structure you see in the sky today, every galaxy, every star, every planet, originated from those tiny ripples in temperature visible in the CMB. You came from those ripples. The atoms in your body were forged in stars, but those stars formed in galaxies that grew from the density fluctuations preserved in that ancient light. And here's something to think about. The CMB photons that we detect today have been traveling for over 13 billion years. They've crossed the entire observable universe to reach us. When they last interacted with matter, there were no stars, no galaxies, no planets, no life. Just a hot, glowing plasma cooling in the darkness. Those photons have witnessed the entire history of cosmic structure formation. And now they're ending their journey by hitting a detector on a satellite or telescope we built. We've captured messengers from the dawn of time. Number 4. Dark energy. The force tearing everything apart. For most of the 20th century, astronomers assumed the universe was slowing down. Gravity, they figured, would gradually pull everything back together. Maybe the universe would eventually stop expanding and collapse back in on itself in a big crunch. Or maybe it would expand forever, but at a decreasing rate. Either way, gravity was supposed to be in charge, slowing things down. Then, in 1998, 2 teams of astronomers made a discovery that changed everything. They were studying distant supernovae, explosions of dying stars that can be used as standard candles to measure cosmic distances. What they found shocked the scientific community. The universe isn't slowing down, it's speeding up. The expansion of space is accelerating, and something is driving that acceleration. We call that something dark energy, and it makes up about 68% of the total energy content of the universe. Think about that. More than 2/3 of the universe is made of something we know almost nothing about. We can measure its effects. We can see that galaxies are accelerating away from each other, but we don't know what it is. Is it a property of space itself? A sort of vacuum energy that pushes space apart? Is it a new kind of field permeating the cosmos? Is it a sign that our understanding of gravity is incomplete? The simplest explanation, and the one that matches observations best so far, is that dark energy is what Einstein called the cosmological constant. In his equations of general relativity, Einstein included a term that represented the energy of empty space itself. He later called it his biggest blunder because he'd added it to make the universe static, matching the prevailing belief of his time. But it turns out the cosmological constant might be real, just with a different value than Einstein imagined. If dark energy is a cosmological constant, it means that empty space has energy. This sounds weird, but quantum mechanics predicts that even a perfect vacuum isn't truly empty. Particles and antiparticles are constantly popping into and out of existence in what's called quantum foam. These virtual particles could contribute to the energy of space itself. The problem is, when physicists calculate how much energy the quantum vacuum should have, they get an answer that's about 10^120 times larger than what we actually observe. That's not just a little bit off. It's possibly the worst prediction in the history of physics. So we're stuck. We know dark energy exists because we can measure its effects. We know it's causing the universe to expand faster and faster, but we don't know what it is or why it has the value it does. It's one of the biggest mysteries in all of science. The consequences of dark energy are profound and, frankly, a bit depressing. If dark energy continues to dominate, and there's no reason to think it won't, the universe will expand forever at an accelerating rate. Galaxies not bound to us by gravity will drift away, eventually moving so fast that they disappear beyond our cosmic horizon. In trillions of years, observers in our galaxy will look out and see nothing but darkness. All the distant galaxies will be gone, their light stretched beyond detectability. Eventually, even the stars will run out. Star formation requires gas and dust, and once all the available material is used up, no new stars will form. Old stars will die, and the universe will fade to black. This end state is called the Big Freeze or heat death, and it's the most likely fate of our universe. Everything will spread out, cool down, and grind to a halt. Entropy wins. But don't let that ruin your day. This fate is incomprehensibly far in the future, trillions upon trillions of years from now. Our sun will die in about 5 billion years. The Milky Way will merge with Andromeda in about 4 billion years. These events will happen long before dark energy isolates us from the rest of the universe. We've got time. Dark energy is a reminder that the universe is stranger and more complex than we imagined. For all our scientific progress, all our telescopes and satellites and equations, we're still missing the majority of what's out there. Dark energy makes up 68% of the universe. Dark matter makes up another 27%. That means everything we can see, all the stars, planets, gas, dust, people, makes up less than 5% of reality. We're barely scratching the surface. Number 3. The multiverse. Infinite possibilities beyond our universe. So far, we've been talking about structures within our observable universe. But what if our universe isn't the only one? What if it's just one bubble in an endless sea of universes, each with its own laws of physics, its own history, its own fate? This is the idea of the multiverse, and it's both mind-blowing and controversial. The multiverse isn't just science fiction, though it sounds like it. Several different lines of thinking in theoretical physics lead to the idea that multiple universes might exist. One comes from cosmic inflation, that rapid expansion in the first fraction of a second after the Big Bang. Some versions of inflation theory suggest that inflation didn't happen just once. Instead, it's a runaway process that's constantly creating new universes. In some region of space, inflation stops, and a universe like ours forms. But in other regions, inflation continues, and new universes bubble off. This is called eternal inflation, and it suggests that new universes are being created all the time, forever, in a vast multiverse landscape. Another source of multiverse thinking comes from quantum mechanics. In the standard interpretation, when a quantum measurement happens, the wave function collapses and one outcome occurs. But in the many worlds interpretation, all possible outcomes occur, each in its own branch of reality. Every time a quantum decision point happens, and they're happening constantly, trillions upon trillions of times per second, the universe splits into multiple versions, one for each possible outcome. In this view, there are countless parallel universes containing every possible history. Then there's the string theory landscape. String theory attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality are tiny vibrating strings rather than point-like particles. But string theory allows for an enormous number of possible configurations, maybe 10, 500 different versions, each with different physical laws. Some versions have gravity, some don't. Some have 3 dimensions of space, others have 10. If all these configurations actually exist somewhere, that's another form of multiverse. So which is it? Are there multiple universes or not? Honestly, we don't know, and figuring it out is tricky because, by definition, other universes are beyond our observation. If they exist, they're causally disconnected from us. We can't see them, visit them, or receive signals from them. That makes the multiverse idea difficult to test scientifically. Some physicists embrace it as a natural consequence of our best theories. Others dismiss it as untestable speculation that's not really science. But the multiverse does solve some puzzles. One is the fine-tuning problem. The laws of physics in our universe appear to be finely tuned to allow for complex structure and life. If the strength of gravity were slightly different, stars couldn't form. If the electromagnetic force were a bit stronger or weaker, atoms wouldn't be stable. Change any number of fundamental constants by even a small amount, and you get a universe that's utterly sterile, incapable of producing anything interesting. Why is our universe so perfectly tuned? One answer is the multiverse. If there are countless universes with different physical laws, then it's not surprising that we find ourselves in one that allows for life. We couldn't exist in any of the other ones. This is called the anthropic principle, and it's deeply unsatisfying to some physicists because it feels like giving up on finding a deeper explanation. But it might be the truth. Imagine the multiverse as an infinite ocean. Each universe is a bubble in that ocean, floating in a higher dimensional space we can't perceive. Most bubbles are dead, filled with physics that doesn't allow for stars, planets, or life. But every so often, a bubble forms with just the right conditions. And in that rare bubble, galaxies form, stars ignite, planets coalesce, and eventually, life emerges. We live in one of those lucky bubbles, looking out at our patch of reality and wondering if there's anything beyond. If the multiverse exists, the philosophical implications are staggering. It means that everything that can happen does happen, somewhere. Every possible history, every choice you didn't make, every version of you that could have existed, does exist in some other universe. There's a universe where you made different choices. A universe where humanity never evolved. A universe where Earth never formed. The multiverse contains infinite diversity, infinite possibility, infinite weirdness. But it also means we might never know the full truth about reality. We're stuck in our bubble, observing only our own universe, forever cut off from the larger multiverse beyond. It's humbling and isolating at the same time. We might be part of something incomprehensibly vast, but we'll never see most of it. Number 2. Time itself, the unstoppable river. We've been talking about space, but what about time? Time is just as much a part of the cosmic structure as space is. In fact, according to Einstein's relativity, space and time are woven together into a single entity called space-time. You can't have one without the other. And time, it turns out, is stranger than most people realize. Time isn't absolute. It doesn't flow at the same rate everywhere. If you're moving fast, time slows down for you relative to someone standing still. If you're near a massive object like a black hole, time slows down because gravity warps space-time. This isn't science fiction or philosophy. It's physics, confirmed by countless experiments. Atomic clocks on airplanes tick slightly slower than clocks on the ground. GPS satellites have to account for time dilation, or their positioning calculations would drift off by miles. But what is time, really? Why does it flow in one direction, from past to future? Why can we remember the past but not the future? These questions don't have simple answers. The laws of physics, at their most fundamental level, don't distinguish between past and future. The equations work just as well if you run time backward, yet we experience time as having a direction, an arrow pointing from yesterday toward tomorrow. The answer seems to have something to do with entropy, the measure of disorder in a system. The second law of thermodynamics says that entropy always increases in a closed system. Things get more disordered over time. A broken egg doesn't spontaneously reassemble itself. Heat flows from hot to cold, never the reverse. This increase in entropy gives time its direction. The future is the direction in which entropy increases. But why did the universe start with such low entropy? The Big Bang was a state of incredibly high order. All the energy and matter concentrated in a tiny space. Since then, the universe has been spreading out and getting more disordered. But why did it start ordered in the first place? That's one of the deepest questions in cosmology, and we don't have a satisfying answer. Time might even have a beginning and an end. The Big Bang marks the start of time as we know it. Before the Big Bang, the concept of before might not even make sense. Time itself could have begun with the universe. And if the universe continues to expand forever, driven by dark energy, time will continue infinitely into the future. But if dark energy changes, or if the expansion eventually reverses, time could have an endpoint, a moment when the universe collapses back on itself and time stops. Then there's the question of whether time is fundamental or emergent. Some physicists think time is a basic feature of reality, woven into the fabric of space-time. Others think time might emerge from something deeper, something more fundamental that we don't yet understand. In some theories of quantum gravity, time might not exist at the most basic level. It might be an illusion, a useful concept that emerges only when you look at the universe on large scales. Time is also deeply connected to consciousness. We experience time as flowing, as having a present moment that moves from past to future. But physics doesn't include a present moment. The equations treat all of time as equally real, a four-dimensional landscape where past, present, and future all exist together. This is called the block universe view, and it suggests that our experience of time as flowing might be an illusion created by our consciousness. If the block universe is correct, then everything that has ever happened and everything that will ever happen already exists, laid out in the space-time continuum. The moment you were born still exists in the past. The moment you'll die already exists in the future. You're not moving through time. You're a four-dimensional object extended through space-time, and your consciousness is just experiencing different slices of that object, one after another. It's a weird and unsettling idea, but it might be true. And if it is, it changes how we think about free will, causality, and our place in the universe. Are our choices real, or are they predetermined, already existing in the block? Philosophy and physics collide when we think seriously about time. Number 1. Existence itself. The ultimate question. We've covered some of the largest and strangest objects and concepts in the universe. But there's one thing bigger than all of them. One question that dwarfs every mystery we've discussed. Why is there something rather than nothing? The universe exists. You exist. Stars exist. Galaxies exist. Space and time exist. But why? Why does anything exist at all? Why isn't there just nothing? No matter, no energy, no space, no time, no laws of physics, just absolute total nothingness. This is the deepest question in philosophy, and perhaps in all of human thought. Science can tell us how the universe works. It can explain how stars form, how galaxies cluster, how the universe evolved from the Big Bang. But science struggles with the why. Why these laws of physics and not others? Why does the universe bother to exist? Some people turn to religion or philosophy for answers. Maybe a creator or some transcendent cause brought the universe into being. Maybe existence is necessary somehow. Maybe nothingness is impossible and something had to exist. Maybe our universe is part of a multiverse, and existence is just a brute fact with no deeper explanation. But here's the thing, even if we had an answer, even if we knew why the universe exists, that answer would itself exist and would require an explanation. It's turtles all the way down. Every explanation depends on something prior, something more fundamental. And you can keep asking, why, forever. At some point, you hit bedrock, something that just is, with no further explanation. Maybe the universe is that bedrock. Maybe the laws of physics are self-explanatory somehow. Maybe they had to be the way they are. Or maybe there is no ultimate explanation. Maybe existence is a brute fact, and asking why it exists is like asking what's north of the North Pole. The question doesn't make sense. And yet, we can't help but ask it. Humans are the universe asking questions about itself. We're made of atoms forged in stars, arranged in patterns complex enough to wonder, to think, to look up at the night sky and ask, why? We're cosmically insignificant, tiny specks on a small planet orbiting an average star in an ordinary galaxy in an incomprehensibly vast universe. And yet we're also cosmically significant because we're the part of the universe that's become aware of itself. Every person who has ever lived has looked up at the night sky and wondered. Our ancestors wondered if the stars were gods or spirits. They created myths to explain the cosmos. As we learned more, the myths gave way to science, and the universe revealed itself to be stranger and more wonderful than any myth. We discovered that the Earth isn't the center of everything, that the stars are suns, that galaxies exist, that the universe is expanding, that dark matter and dark energy fill the cosmos. Each discovery pushed back the boundaries of the unknown, but the ultimate mystery remains. Why is there something rather than nothing? We don't know. We might never know. But we keep looking, keep asking, keep exploring. And in that search, in that endless quest to understand, we find meaning, we find purpose. We find connection to something larger than ourselves. You are part of this universe. You are a way for the cosmos to know itself. The atoms in your body were forged in stellar furnaces billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe were all created in the hearts of dying stars. You are, quite literally, made of stardust. And for a brief moment in cosmic time, those atoms have come together to form you, a conscious being capable of looking back at the universe and understanding where you came from. That's miraculous in its own way. The universe began as a hot, dense state 13.8 billion years ago. It expanded, cooled, formed atoms, then stars, then galaxies. Some of those stars exploded, seeding space with heavy elements. Those elements came together to form planets. On at least one of those planets, life emerged. That life evolved, became more complex, developed consciousness, built civilizations, created science and art and philosophy. And now here you are, reading these words, thinking about the cosmos, participating in the universe's grand story. So yes, we've talked about enormous structures, The Sloan Great Wall, Stevenson 2-18, the Boötes Void, Sagittarius A*, the Great Attractor, the Cosmic Microwave Background, Dark Energy, the possibility of a multiverse, the nature of time, and the mystery of existence itself. But the biggest thing of all might be the simple fact that we're here to contemplate these mysteries. Against all odds, in defiance of entropy, in a universe that seems indifferent to our existence, we persist, we wonder, we seek, we try to understand. The universe is vast, ancient, and strange beyond comprehension. And yet, for this brief moment, we get to be part of it, to experience it, to marvel at it. That's something worth cherishing. We're children of the cosmos, looking back at our cosmic parent and trying to understand where we came from and where we're going. The journey of discovery continues, and each answer we find opens up new questions, new mysteries, new horizons to explore. So keep looking up, keep asking why, keep seeking the truth wherever it leads. Because in the end, the search itself is what makes us human. The search is what gives our fleeting existence meaning in the face of cosmic vastness. And who knows, maybe one day we'll finally understand why there's something rather than nothing. Or maybe that question will remain forever beyond our grasp, a reminder of our limits and our ambitions. Either way, we're here. The universe exists. And for now, that's enough.